In the first lecture on feedback, I listed a number of consequences on the amplifier properties. The sixth consequence was stability. So it was just mentioned that if you put an amplifier in a negative feedback, then it increases the stability of the amplifier. So today we will study what do you mean by stability, and then we will see that how this under which condition in the negative feedback amplifier will not be stable, and then we will try to find out uh, or define few parameters using which by calculating those parameters we will be able to see if our amplifier in a negative feedback is going to be stable or not. So here we have a technical word, stability. So given an amplifier or in general any circuit, what do you mean by stability? So actually there is no rigorous and universally accepted definition, but qualitatively and widely accepted meaning of this stability is that if you have a network and if you give finite input or bounded input, if it results in bounded, that means finite, then we say that this circuit is stable. So now if we take a more specific scenario, that means we have an amplifier and we are giving a step input. So value suddenly changes from this lower value to high value, and then maybe it remains there like this. So this is Vi that we are giving. So what are the possibilities of output? What are the different types of output that can happen in real life? And out of those possibilities, which one we will call as stable case? That means we will label the amplifier as stable, and in which case we will say it is unstable. So ideally, what we should get here is again a step response, but of course with a larger jump. So this is the ideal output, right? And if we have t is equal to 0 here, so this will also be at t is equal to 0. Jump occurs at t is equal to 0, or maybe even some delay also can be accommodated. But what happens in real life, practically, there will be four types of output. So first case is that the output changes from low value to final stable value here, but it changes over a certain duration and change is gradual. So here also we can see that we again have a step output, but it is not ideal step output. So this is first case. Second case is that we again have output which starts from 0 like previous case, and ultimately it also settles to the same value, say Vp, but before it attains that value it undergoes what is called ringing, like this. So it takes now maybe more time to settle to that value, or maybe even smaller. That is not important, but it finally attains that value. Third possibility is that it shows this ringing, but this ringing never dies out, and it is of constant value, like this. So this value, this remains fixed. And the last possibility is, you can say, the escalation of even this third one. That means output does not remain bounded. So here we have a output which is growing with time. So these are the four major classes of output that we can get for a step response to an amplifier. So out of this, the first two cases, this case 1 and case 2, these two response, they will be called as the stable response, and we will see that amplifier is stable for these two cases, and for these two cases we will say that we have unstable amplifier. So now we have already seen this kind of response. In fact, this response is called oscillatory, and any circuit which produces this type of response, the third response, will be called as oscillator. So we have already studied oscillator, and we will start with that topology. So in the oscillator, we have amplifier, and then we have a feedback network, and output of feedback network in general is added with the external input, and then we get external output. And in this case, we will carry out the subtraction of this feedback from the external input. So for this case, we have already carried out the analysis, and we found the transfer function to be given by this ratio. So whenever we have negative sign here, we will get a positive sign here in the denominator. So recall that we considered this third case as unstable output. So now we want to study this feedback with respect to that kind of scenario. So we have already studied, and we found that if this denominator is 0, that means 1 plus beta A is equal to 0, then we will get output even for this is not equal to 0, even for x is equal to 0. So we say that our system is unstable. So from here we find that if beta A is equal to -1, then we have, this implies unstable feedback amplifier. So this amplifier which we have put in feedback will become unstable. and this we call Barkhausen criteria. So here important thing to note is that the uh, beta A magnitude is 1 and phase is minus 180 degree, or maybe even plus also. So why this become unstable? Here we can see that if we give any sinusoidal input here, then initially we get the same sinusoid input here and it gets amplified and appears here with larger amplitude. And here we have taken inverted version because we will consider K to be uh, positive. Sorry, this beta to be positive for positive. So if beta is positive, this negative sign with the loop actually gets associated here with the A. And now you can see that the beta will give a fraction of this, and this is going to get subtracted from this input. That means basically this will get added, and what we will get here is a now a larger signal. So if the larger signal is fed to the amplifier, you will get a still larger output like this. So here this will lead to even larger feedback, then even larger input, and so this phenomena will grow on. So what is happening here is on the input side, addition of the feedback signal is taking place with the external, and that is causing the instability. So we will study this in more detail, graphically and mathematically also. And for that, we will try to keep the thing simple. And here we have assumed beta to be positive. We will add one more constraint, that it is real as well. So this feedback is positive and real. So here this implies that beta is equal to -1 implies that now the phase of A is equal to minus 180 degree, because the phase of this beta is going to be 0 degree. It is a real and positive. So if we have an amplifier whose phase is minus 180 degree at certain frequency and beta is real, then it will become unstable. So now we will be more specific, and we will take amplifiers of various order, first order, second order, third order, and put it into negative feedback loop, and then try to see that which of the amplifier will satisfy this Barkhausen criteria, and or alternatively which type of amplifier will give rise to this beta A is equal to minus 180 degree, or the amplifier itself maybe. So first we will take a first order amplifier, and suppose this amplifier is put into negative feedback. So what we have to see is whether there is a possibility of the phase of the amplifier to become minus 180 degree at any frequency or not. If it shows this possibility, then this amplifier in a negative feedback might become unstable under suitable value of beta. So here we are going to take the transfer function AS like this, A0 divided by so this is a first order amplifier, and this will be put into negative feedback. So we want to know whether it will be ever unstable or not. So we can see that the transfer function is going to be like this. Here is omega P1, the pole, and the phase response for this case is going to be like this. it will start from, we know that 0, and it will attain maximum value of 90 degree. And it will attain this value of 45 at this value. Yeah. So it attains 90 degree, that too at omega is equal to infinity. So here we see that the phase of A maximum value is equal to minus 90 degree at omega infinity. That means if you put a first order system, first order amplifier in a negative feedback with beta real, so it will never oscillate. It will always lead to a very stable system. And this is the reason why, if you see the frequency response of 741, it has a first order response. So here is a frequency response of LM741, the most popular amplifier that we use in our lab. So here you can see we have x-axis and y-axis is the magnitude of the open loop transfer function. And we see that from 3-4 hertz it starts decaying, and it attains 0 dB at 1 megahertz. So here you can see that we have a pole at 4 hertz. So this is a first order system, and if you put this thing in a negative feedback, and that is what we do with the when we design a inverting or non-inverting amplifier, we put a negative feedback with the help of 2 resistors. So that amplifier will never oscillate. That means it will always be stable. And this is one of the key reasons for the popularity of 741. Now let us take amplifier of second order. So in this case, transfer function is going to be A naught as divided by omega P1 plus 1 as divided by omega P2 plus 1. So here the transfer function will be like this. This is omega P2, this is omega P1, 2 poles. And each of the pole will give rise to phase shift of 90 degree. So it starts from 0. We have minus 90 degree and then minus 180 degree. So first pole will give rise to frequency response like this, phase response like this. So this is the phase of A. So it starts from 0, attains minus 45 degree at omega P1, and then omega P2 gives rise to another decrement by 90 degree. So finally we have 180 degree phase, but at omega infinity. So here we are able to achieve phase of A is equal to minus 180 degree, but at omega is equal to infinity. So it might appear that it will oscillate at omega is equal to infinity, although that frequency definitely is never going to occur in the real life. But keep in mind that this is one requirement. Second requirement is that beta A magnitude should be equal to 1. So there are 2 requirements, 1 and 2. Then only oscillation will take place. So even if we are able to theoretically satisfy this first condition, you can see that second condition will be hard to satisfy, because here you can see that this is A. So A itself has become 0 dB at some finite frequency here. 0 dB means magnitude of A has become 1. So that means beyond this frequency, magnitude of A is less than 1. And typically beta is also going to be less than 1. So at omega infinity, beta A is definitely going to be less than 1. In fact, it will be very, very small because this point where 180-degree phase occurs is very far off, and by that time this A must have decayed to very small value. So even if this condition is getting satisfied, first one, this will not get satisfied. So the second order amplifier, if used in real life with real feedback, will also be stable. But you can see that there is a bit of risk involved. Now let us take a third order amplifier. If you take third order amplifier, then the transfer function is A0 divided by S by omega P1 plus 1, S by omega P2 plus 1, S by omega P3 plus 1. So there are three poles. So the magnitude response is like this. So we know that these are minus 20 dB per decade. By the way, this slope is also called minus 6 dB per octave. So both are the same slope. So here octave means 2 times. And here decade, we know that 10 times. So when frequency increases by 10-fold, decrement will be minus 20 dB. However, if frequency increases by 2 times, decrement will be only minus 6 dB. So ultimately, we will have here minus 60 dB per decade. So this is the magnitude. And what will be the phase? So each of the poles will ultimately give rise to 190 degree, and finally there will be a total of 270 degree phase shift. So this is due to the first pole, this will be due to second, and then this will be due to third one. So here we can see that there is a possibility of phase becoming 180 degree at some finite frequency. Here. So here we see that phase of A might become 180 degree at finite omega. Not only that, here we see that at this frequency, the magnitude is greater than 1. So one can have a beta less than 1 such that beta A magnitude is equal to 1. And it might, in fact, it will oscillate. Implies that if you put this in negative feedback, the amplifier will become unstable. So a third order system will definitely lead to instability. Now to talk about this instability, we define two technical parameters. They are called crossover frequencies. So under this frequency, there are two different types of frequency. One frequency is called phase crossover frequency, denoted as omega px, and definition of this frequency is it is a frequency at which the loop gain omega px phase will be equal to minus 180 degree or even plus also. So second frequency is gain crossover frequency, and this is designated as omega gx, and this is a frequency at which the magnitude of this loop gain is equal to 1. And since we typically plot this loop gain in dB, so 20 log, or you can say beta A in dB is going to be 0. So now we will talk about the stability of amplifier in terms of these two frequencies. So let us consider the case where we have 20 log mod beta A, and suppose the response is something like this. So we are showing only the part of the response, not the complete response. And if you see the phase response, then suppose it is like this one. Here. So what we see is there is a frequency at which phase becomes 180 degree. So you can say that this is the phase crossover frequency, this point. And the gain crossover frequency is going to be this one, omega gx. So here we see that we have a scenario when the phase is equal to 180 degree at frequency, and beta A is greater than 0 dB, that means greater than 1. So in this case, there will be more feedback and the amplifier will be unstable. And here, even if you reduce this beta, this will at the base will become equal to 0 dB, that means 1. And this reduction of beta is not going to affect the phase because we are assuming beta to be positive and real. So this system or this amplifier which is shown here is going to be unstable. Now if you see a different case where we have this as the so this is 180 degree, That means this is omega px, phase crossover point, and then we have this kind of response for the magnitude. So now this omega gx is smaller than omega px. So here we see that when the phase is 180 degree, that time the magnitude is less than 1 here. So in this case, beta A is less than 1, although the phase is minus 180 degree. So in this case, system is going to be stable because it will not fulfill the Perkausen criteria. So from here we find that whenever gain crossover frequency is on the left side of the phase crossover frequency, that means for stable operation, the gain crossover frequency should be less than phase crossover frequency. So in this case, beta A will never be equal to 1 and it will not oscillate and it will be stable, but here it is going to be unstable in the first example. Let me point out that this stability that we have arrived at, condition for the stability, is based on the Bode plot, and actually this is not completely or rigorously accurate. This does say a lot about the stability, but more rigorous condition is obtained from what is called Nyquist test. So, but for the first hand analysis, this is quite good enough. So now we will take an example and then try to see that when the amplifier becomes unstable. So let us take a well-known common source amplifier, and we have already seen that it is the third order amplifier which will become unstable at a finite frequency. So we are going to consider third order amplifier, and to create a third order we will take three common source amplifiers, and to induce the frequency dependency we will assume that load is capacitive. So here we have one common source amplifier which is loaded capacitively, and we are going to uh, cascade three such amplifiers. So all these three stages are identical. They have same capacitive load and resistive load. So we want to know that if this is put in a negative feedback loop with say beta is equal to 1, then at which frequency this is going to oscillate, or rather what should be the condition so that it doesn't oscillate. So here first we will have to find out the transfer function of this amplifier. It's a transfer function. So here we have three stages: stage 1, stage 2, stage 3, and gain for stage 1 is going to be minus GM ZL. where ZL is the complex load. And to keep things simple, we will take lambda is equal to 0. So for one stage, which is this one, here we see that RD and this C, they are in parallel, so they form a complex load. So ZL is going to be RD divided by 1 plus SC RD. So this is going to be the transfer function of the one stage. So overall transfer function is simply going to be 3 cube of this one. So this is going to be minus GM cube RD cube divided by 1 plus SC RD whole cube. So here we find that the DC gain is going to be minus GM RD cube and whole is going to be 1 by C RD. So this is the amplifier, and this will be put in a negative feedback, and we want to know at what frequency this will be unstable, and alternatively to make it stable, what should be the condition on GM and RD. So this is the gain of the overall amplifier for one stage. It is going to be minus GM RD. So if you see the transfer function will be like this, with a slope of minus 60 dB per decade. And this is the magnitude of the transfer function, overall transfer function. And here we have omega p. And the phase, you can see, is going to be vary from 0 to minus 270 degree. So first we will have to find out what is the phase crossover point. So here the phase of the first order transfer function is going to be minus tan inverse omega by omega p. So this is of 1 CS. So the overall phase response is going to be 3 times of this one, because 3 such stages they have been cascaded. So the phase going to be tan inverse is going to be minus 3 tan inverse omega by omega p. So we know that the omega px, the phase crossover frequency, is frequency where this quantity becomes equal to minus 180 degree. So the omega px is equal to minus 3 tan inverse omega px by omega p equal to minus 180 degree. So this implies tan inverse omega px by omega p is equal to 60 degree, and if we solve this, omega px by omega p is equal to square root 3. So omega px is square root 3 into omega p. So this is the phase crossover point. Now at this frequency, what we should have is gain less than equal to 1. If the gain at this frequency is less than 1, then this amplifier, if it is put in a negative feedback with k beta is equal to 1, then it will be stable. So for stability, A at omega px should be less than 1. So this implies gm cube rd cube divided by square root of 1 plus omega px by omega p, it should be less than 1. And this quantity we have already found out, it is equal to square root 3. So this says gm cube rd cube divided by square root of 1 plus square root 3 square whole cube less than 1, implies that gm rd cube is, so this is going to be 2 cube less than 1, implying that gm rd less than 2. So if the gain of one stage is less than 2, then in a negative feedback with beta is equal to 1, the amplifier will be stable. So this was with beta is equal to 1. So one can choose a beta smaller than 1. In that case, for say beta is equal to 0.75, what you will have to do is ensure that beta A is less than 1 at omega px. That means 0.75 into A less than 1. So this will then give rise to gmrd cube by 2 cube less than 1 by 0.75. So this time it is going to be gmrd less than 2 by cube root of 0.75. So now we can take a larger gain. So we found that if we have omega gx gain crossover less than omega px, this implies stability. So we can have two systems where both they are satisfying this condition, and we would like to know that which one will be better. Say for example, we have a feedback system like this. So here is omega px, this is omega px, and here we have omega gx. So we see that it is fulfilling this requirement. Now we have another system where again this condition is fulfilled. Omega px, omega gx. So again we have system which is fulfilling that condition. So which out of these two one will choose? So here we see that in this case, in the case A, the difference between omega gx and omega px is not much. That means this beta A, although it is less than 1 at omega px, but not very small. But if you see the system B, then here beta A is going to be really very small at frequency where phase becomes minus 180 degree. So in this case, this is system B is going to be more stable, and this is going to be relatively compared with B less stable. So what will be the scenario in terms of output? That means if we have this feedback system here, so this is with the negative feedback, and if we give step response here, what we will get on the output side is a response like this. That there will be ringing, and then finally the output will settle. But in this case, we have the same feedback system, and again it is excited by exactly same step. So what will happen here is ringing will be much less, or in fact if gap is very large, then it will settle like this. Yeah. So we say that there is a relative, there is a degree of stability between these two systems. So one system is more stable compared with the other one. And this relative stability is actually dictated by the gap between these two frequencies, gain crossover and the phase crossover. Now to convey this relative stability, we quantify it with the help of two parameters. One is called phase margin. So phase margin is defined as the phase of amplifier at gain crossover frequency plus 180 degree. So let us try to see that what exactly is going to be this for the above two cases. So what we will have to do, we have to note down the gain crossover frequency, find the phase of the amplifier, and then add it to 180 degree. So here what, because beta is real, so phase of beta is also going to be same as phase of A. So here we can say this is phase of A, although it is actually beta A. So here you can see that we have to find out phase at gain crossover point. So it is going to be a certain negative value. And because this omega gx is more and more on the left hand side, so this phase is going to be smaller and smaller in numerical value, but of course with the sign. So now if you add, say for example, in this case, it could be say minus 40 degree. So now if you add this 40 degree with 180 degree, so you are going to get 140 degree. However, if you take the first example, example A, so in this case, the phase is going to be, say, for example, 90 degree, minus 90 degree, because it is closer towards the omega px, that means closer towards the 180 degree point. So in this case, you can see that the phase margin, this is the phase margin, is smaller compared with the case B. So this is PM. So if you have a system, you simply calculate PM, phase margin, and if you find that if it is large and if it is larger and larger, it will be more and more stable. So this is one way of comparing or pointing out the relative stability of two systems. Second parameter that uh, we use to again convey the relative stability is gain margin. So gain margin is defined as 0 minus 20 log of magnitude of A, or rather beta A. So let us see that what exactly this quantity says and how it conveys relative stability. So here we see that and keep in mind that this is calculated at omega px. So the frequency where phase is equal to 180 degree. So now here this one is omega px. So here we have omega px, and at this point what we will have is this is so this is a beta A axis, this one, and this is zero value, and this whole thing is gain margin. So we see that beta A is this value at omega px. But if you see the case 1, then for case 1, we have this much of GM. So value of beta A at omega px. So here again we see that if GM is larger, for example in case B, the system is going to be more stable. So here we can see that GM larger implies more stability. So one can calculate these two parameters and convey the relative stability, that which of the two system is more stable, and one can at the design level choose how much of phase margin or gain margin they want to incorporate in the system, so that even in the when parasitics come into picture, system will be stable. And the references are Rajavi and Sidra and Smith.